Okay, welcome to Electroanalytical lecture number 4. This is on electrolysis and electrodeposition, and this is going to largely focus on techniques that measure current to ascertain the concentrations of analytes. And the reading list hasn't changed, and it's not going to change. Previously, we've discussed techniques which analyze a solution's composition by measuring potential difference. These can detect Faradaic or non-Faradaic processes, but the current passed is always minimal. Electrodeposition and electrolysis both require significant current to flow to drive the processes, and the potential is provided by an external supply. In the example shown, copper is reduced by electrons produced in the oxidation of water at the anode. The purpose of the external supply is to elevate the energy in the Fermi level of the electrode. So in the example shown, the Fermi level on the left hand side is lower, and the activation energy for electron transfer to reduce the hydronium ion and produce H2 is too high for it to be a spontaneous process. Now, in the example on the right, a potential has been provided, and the Fermi level has been elevated, and now you can see the activation energy is overall much lower, and the reduction can take place. As a result, appreciable current will flow. This means that the charge transferred is proportional to the conversion of reactants to products. And the current, which is the rate of charge transfer, is proportional to the rate of reaction. So by way of a worked example, we know that moles reacted is equivalent to the current times the time the current has been applied for over NF, where F is Faraday's constant and N is the number of electrons transferred in the reaction being considered. How long will it take to deposit 100 milligrams of copper on the electrode if a current of 170 milliamps is applied? Now, we'll go through the answer to this and the way to approach one of these questions in the lecture, but this would be a good thing for you to try and work out on your own beforehand. So when carrying out an electrolysis or an electrodeposition, we know the magnitude of the potential that we've applied, but we still need to measure the overall potential to account for all the other potential contributions due to the processes taking place in the cell. If we use a standard working electrode like silver chloride, it will rapidly become polarized like the working electrode when appreciable current flows. Now, in the case of a standard reference electrode such as silver chloride, this means its potential is no longer consistent. To avoid this, the working electrode and the reference electrode are connected in parallel through the potentiometer or the voltmeter, and the bulk of the current then flows between the counter electrode, a third electrode put in to carry the charge, and the working electrode, which is the electrode where the reactions we are interested in are taking place. Due to the high resistance of the voltmeter, an appreciable current now does not flow between the reference electrode and the working electrode, and the reference electrode does not become heavily polarized. The 3-electrode cell then is used in all types of analytical electrochemical experiments where there is a significant flow of current. So, developing the idea of electrodeposition, we'll look at electrogravimetric analysis. Electrogravimetric analysis involves electrodeposition of the analyte onto an electrode with a large surface area, in this case a fine platinum gauze electrode. The electrode is subsequently weighed to determine the gain of mass due to the deposition of analyte. Oxidized or reduced species can be measured simply by selecting positive or negative polarity at the wire gauze to cause them to be oxidized or reduced. The endpoint is determined either by a color change in the solution, or you can lower the electrode slightly for a few minutes to expose some of the bare metal surface and watch to see if any more of the analyte becomes deposited. If it does, you can lower it again a little bit more. If it doesn't, then you know that the supply of analyte in the solution is exhausted. The observed current voltage behavior for the reduction of copper 2+ from a solution of copper sulfate in perchlorate is shown. The electrolyte is purged with N2 gas so that oxygen reduction doesn't interfere with the measurement. The plot here illustrates that a significant overpotential needs to be applied above the standard electrode potential of -0.911 volts for charge transfer to be able to commence. Approaching -5 volts reduction of water occurs, showing a sharp upturn in current as it becomes feasible, and this overwhelms the current from copper reduction. Now this is a good practical illustration of how it's crucial to overcome both the internal resistance of the cell, IR, and the overpotentials, which are largely due to activation barriers and transport, before electrolysis or electrodeposition happens at a detectable rate. The next technique we consider is coulometry. This is based on the principle of counting the electrons consumed in a reaction. In one half of the apparatus shown, a constant current generates Br2 from Br- in solution. Charge passed at constant current is proportional to the amount of the Br2 generated. On the right hand side of the reaction vessel is a detector. This passes a much smaller current, only sufficient to detect the presence of Br2 without significantly changing the concentration of Br2. An analyte, in this example cyclohexene, is added through the ground glass stopper into the reaction vessel, where it's brominated in an addition reaction catalyzed by a small amount of mercury acetate. This consumes the Br2 generated and the detector current falls. Once all the cyclohexene has reacted, the detector current increases in response to the excess Br2 and the coulometric current is stopped. The charge passed in the time taken for the reaction to reach completion gives the number of moles of Br oxidized. Hence, the number of moles of Br2 generated before the cyclohexene was completely consumed are known, and we can calculate the amount of cyclohexene added. Amperommetry involves measuring the current passing between two electrodes that are involved in an electrolysis. The current is proportional to the concentration of analyte, and the relationship is determined by calibrating the probe with solutions of known analyte concentration. By way of example, the Clark oxygen electrode is used to measure dissolved oxygen in solutions. A small plug of silica permeable to oxygen is positioned at the tip of a glass casing. When dipped into the analyte solution, oxygen diffuses into the filling solution. A platinum electrode, often tipped with gold to limit fouling, is the cathode, and it's held at a constant potential between -0.6 volts and -0.7 volts relative to the silver chloride anode, the exact potential being dependent on the electrode configuration and the application. The two half reactions shown below take place. The reduction of oxygen to give water and the oxidation of silver to produce more silver chloride. The current is measured in a series of standards to calibrate the current response to O2, and a graph of current versus O2 is constructed. The current of the unknown is then referenced to the graph to determine its O2 concentration. Okay, now we're going to look at the rotating disk electrode. So an analyte species can approach an electrode by one of three modes of transport. First of all, diffusion. That's the natural movement of a species from an area of high concentration to low concentration. Convection. This is where you force the diffusion by agitating the solution in some way, stirring or heating. And migration. Now this is the movement due to attraction or repulsion caused by charges on the ions and their surroundings. At sufficiently high potential, the reactant is reduced and oxidized so rapidly to reduce its concentration at the surface to 0. And then there is a diffusion gradient between the surface and the bulk concentration being C0. Obviously the surface concentration in this instance is very much lower than in the bulk. Now this rate of diffusion to the electrode limits the rate of reaction. Now the point of the spinning disk electrode is there's a polished electrode surface that spins rapidly and creates a vortex, and this ensures the supply of analyte to the surface, and it also ensures that the rate of reaction is proportional to the current and to the concentration of the bulk. The concentration in the bulk. So the limiting current, so the current that we achieve at the point where increasing the potential no longer increases the current, is largely due to the diffusion current, and this is largely proportional to the concentration in the bulk. So in this example here, the potential of the rotating disk electrode rotating at 2000 revs per minute is swept from a negative voltage to a positive voltage. At around 0 volts, the current begins to increase as the overpotential required to drive the oxidation is met. Cyanocomplex Fe2+ is oxidized at the electrode to Fe3. At around 0.4 volts, the current levels off, no longer increasing with voltage. This is known as the limiting current, and it represents the point at which reactant can no longer be supplied to the electrode any faster. The rotating disk electrode ensures the supply is rapid enough that the transport to the electrode through the now very thin diffusion layer is due to only diffusion and is proportional to the bulk concentration, the bulk concentration being the point of our analysis. So the measured limiting currents of the known standards can then be plotted against concentration to obtain a calibration curve, and this can be used to quantify the analyte in unknown solutions from the limiting currents obtained for these unknown solutions. Okay, so that's the final slide for this lecture. There's one more lecture to go, and it will be on voltammetry.